Hello, everyone. Welcome to our Queen Errata Hall, where we'll talk about different topics across for the whole day and the next day. And my name is Andrei. I will be hosting today. And I work at DDoS mitigation service provider, and our job is to process everything fast, either packets or requests or whatever. And that's why our first topic today is of particular interest for me. And please welcome Ignas Bagdonas, who will talk about vectorization.
Right. Good morning. Thanks a lot. Good morning, Yerevan. Good morning, the rest of the world who are following us online. The powers that be decided that I get the first slot and to a level, try to open up the day and set the bar. Well, we'll see how successful I am with that. But my goals and intentions are a little bit different. We'll talk about things closer to the low-level aspects, the hardware, and all those. Well, somebody seems like they don't like hardware at all. Well, that's fine. So, high load. High load comes in a multitude of different shapes, shades, flavors, aspects, components, ideas, systems, frameworks, and whatnot. And we have 2 quality days here to spend talking about a multitude of those aspects in different details, in different contexts. With different applications, a level of depth, and everyone has an ability to choose whatever set of interests they would like to go deeper into. And yes, there's really a large amount of different sets of technologies and topics to discuss here. Certainly everyone can find something of interest. Now, you might guess what is common around all of those code poetry or code prose examples that we have here on the screen. In fact, that's simpler than it might look like. The common part is the quality source code, which has to meet a compiler infrastructure at some point in their lifetime. Right? And the compiler does the magic, and the end result of that goes to the hardware. And it's the hardware which runs all of those beautiful components in one or the other way. So we will try to focus over this brief presentation about the lower right part. Well, not exactly about that specific lower right part, that's history. But the topic itself is about one of the aspects of contemporary modern hardware operation, that's vectorization. So first thing, who I'm the one to talk about all of this? Well, by day I'm a network engineer or a network plumber. Maybe that would be a more correct way to attribute to myself, and the one who has some understanding and interest about both hardware and the software. So you can think of me as being multilingual in BGP, in Verilog, in C, and in all sorts of things related to that. And my focus is mostly on the system-level design aspects of components which are dealing with packets. So the more packets and the less seconds combined together, that's where I find the beauty in my activities, right? So as more packets per second as possible. So generalizing, that's about, as simple as routers, packet forwarding platforms, and things like that. Well, and this is a compilation of various fragments that I have encountered in systems that are more or less at varying degrees of production use. And we'll briefly go through that in the form of questions, answers, or examples. So the context of this talk, what it is about. If we look at the contemporary general-purpose compute platforms, they have evolved in a multitude of directions. One, the initial scalar approach, where one instruction deals with one set of data that's still there, and that's, well, you all perfectly know the backwards compatibility of x86. And yes, specifically we are talking about x86 here over this presentation, and just very carefully looking into some other alternative platforms. So that's a 40 plus years history. The other direction of platform evolution is specific acceleration functions, specialized instructions for doing well, hard, difficult, heavy, or often required instructions, or simply the acceleration of some specific tasks. And the third direction, which is the focus of here, is vectorization. Basically, a really simple approach which gives another breadth and the latitude of performance into what you already have. Not a new concept as such. It has been with us for around a quarter of a century. If you here remember Pentium 1 MMX, that's how it all started. Since then, there was a multitude of generations of compatible and not so compatible or completely incompatible extensions and experiments coming from the x86 platform vendors. And what we have today is a reasonably good set of functionality, which has been wrapped in a non-insignificant amount of misconceptions, myths, plain lies, fear, uncertainty, and other, say, negative context stories. Yet on the other hand, if you, most of you probably have laptops, x86-based laptops over here. Well, sorry, Mac guys, I don't want to insult you at all, but that's not necessarily the topic of discussion here. So your contemporary laptop has this functionality inbuilt. Well, you have already paid for that. Whether you are using that, that's an open question, and we'll try to look into this. So from my side, I would have kind of two directions. One is to disseminate a little bit of the misconception that vectorization is a domain of high-performance computing only. So, in a sense, if you are not doing simulation, large-scale fluid dynamics or airflow or earthquake type of simulations, then it's not for you. No, not necessary. The other aspect is that how to use those extensions and functionality mechanisms without actual damage to the overall performance. And well, believe me, that happens more often than you would wish. So what is vectorization? A really simple construct. You take the scalar approach to instruction execution and data processing. That means one instruction, one set of data. And you leave aside the instruction part, but you just increase in parallel the data part. So instead of providing the same operation on one set of data in a vectorized context, you apply the same operation, that's the key part, to multiple sets of data. Seems really trivial, and in fact it is. That's nothing too complex. However, the complexity lies in the details. We'll talk about those during the course. Now, this is not new concept as such, and it's not new and not specific to the x86 in general. Half a century ago, at the eras of the mainframes, vectorization was seen as the main mechanism for increasing the performance, and that's where the roots are coming from. So systems like Crays, Control Data, Burroughs, and other historical machines, they actually formulated the majority of ideas used in these contexts. Yes, even today, that is still I probably cannot use the word predominantly, but dominantly the domain of high-performance computation. However, we are seeing very happy trends, so to say, in the overall software industry, and that software vectorization is moving into the masses. What is important to understand when we are talking about the compute system performance is the two dimensions of measuring that performance. That's latency and that's throughput. And those dimensions, they are related, but they don't necessarily intersect. I cannot say that they are orthogonal, but there is a certain degree of freedom between the two. So latency is how quickly you can do something over the interval of time. Throughput is how many of the instances of work you can do in parallel over not necessarily comparable interval of time. So that's basically latitude versus longitude. About the terminology, if we are talking about x86, that's called a SIMD, single instruction multiple data. Well, basically that's the essence of what it is beneath the covers. And my presentation has 3 words in the title. We have covered 1. Now the remaining 2, everyday and practical. So if you want to use something in a practical sense, better those technology components be applicable not only to a very narrow and specific and unique scenarios, but to a multitude of generalized ones. Every day, that's something that doesn't require you, I would use an abused term, rocket science, in order to use it. Well, let's see how can that work. Well, quite often there is a widespread opinion, so why do we need to bother? Well, it's year 2022 today, right? Why we are talking about these low-level things? Compile is a smart tool. You just need to select one of the myriad keyword options, provide that, and it will do the work just fine. That is correct. For certain classes of tasks and for certain applications, compiler will just do the automatic vectorization, and that will just work. Yes, true. And that's typically the domain that is not so much of interest for the general purpose. That's high-performance computing, right? Multiplying matrices left and right, that's certainly what compiler can do very quickly. Doing certain benchmark type of algorithms which the compiler can recognize and is hard-coded for that, and especially the vendor compilers are good at that, so to say good. Yes, certainly can be done, but if you make things look not so trivial, right? You add branching, you add non-trivial operations, you add multiplication, for example, and multiplication is evil in the sense that the end result is way wider than the initial data, and you get the poor compiler complaining, well, sorry, I couldn't do that maybe for good reasons, maybe just because I was a little bit too lazy. But the end result is not necessarily too pleasing. You cannot rely on the compiler toolchain today, if we are talking about the situation today, that it will magically solve all the problem. No, solve all of these problems automatically. Several reasons for that. First, there's a mental shift in the workflow. You need to move away from the control flow into the data flow. There's no branching. There's no specific differentiation of the different options. You mostly are dealing with the linear block of code, which is executed sequentially. And if you need branching or equivalent of branching, you need to translate that into data flow. Some of that can be done trivially, majority of those cases definitely not, and you need certainly to help the compiler with that. Specific implementations, and that's unique to product families. There's also marketing involved. Certain functionalities are artificially positioned into one or other market segment, puts specific restrictions of what you can do and how you can do, and with what parameters and what operations are available for you to choose. You also need to remember the dynamic nature of out-of-order execution platforms. All those rules do apply, just the additional level of interdependency and complexity is added as the layer on top. Now, the remaining part of my presentation is structured as a set of real-world examples in trial and error and eventual success, if any, storylines. And we'll start with Hello Crypto Miners SHA-2. A simple cryptographical hash function used not only for mining bitcoins, but also for a multitude of digital signature systems and things related to that. So a really simple idea. It's a block digest. It operates on fixed length blocks. Takes a block. The block is isolated and standalone from a perspective of relation to other blocks. Does a transformation, gets the state. That state is fed as an initial state into another block. The same process is repeated until you get to process the final message and you get the hash value. There are some details which I think I unintentionally pressed the wrong button. Sorry for that. So the process is rather simple. Yes, it involves a lot of details, but those details are rather trivial to implement. Well, shifting some bits, doing logical operations, there's no multiplication, there are no other heavy instructions, just a large amount of those. In reality, it looks a little bit more complex than that, but we don't look for that. It's not relevant for us in our discussion. So, if we look inside of each of the round of SHA-2, yeah, it starts to look scary indeed. So that's a graphical illustration of what happens there. Well, so you need some shifting some bits and blocks left and right, deciding the majority function, doing some exclusive ORs and things like that. The important and the good news for us is that SHA-2 algorithm operates on a fixed length of the elements. That's 32 bits. That's very nicely matches to our hardware and also nicely matches to the vector length, which is multiple of 32 bits. Overall, SHA-2 and SHA-1 as an example, they are widespread as much that vendors starting provided specific accelerator instructions on their platforms. No, it's not as trivial as you have one instruction which automatically calculates the whole hash. It's not the same as with CRC32, for example. But there are certain instructions which speed up or help you with the latency aspects for calculating the SHA-2 hash. So let's look at some results. We have three options. One is our scalar algorithm implemented. We consider that as a reference implementation. So it runs on a out-of-order speculative pipeline core, all the hardware level optimizations apply, and we take that as a reference one for both latency and for throughput. Then we look into a specific accelerator implementation, so specific SHA-2 instructions. We run it on the same data set with the pre-warmed caches in the same conditions, basically, and we get a rather noticeable increase of performance latency-wise, also throughput-wise. Now, we do we basically get our hands dirty, go into the hardcore low-level coding, and we build a vector implementation for that. The results might look a little bit surprising initially. On the latency side, you lose. That's true, yes, that's correct. But on the throughput side, you have a significant gain. Strange, isn't it? Right, so let's look why it happens like that. So let's take a path of experimenting a little bit and at the same time trying to map those approaches to what our hardware platform can do. We have wide vector register, which happens to coincide in length with the block length of the SHA-2 function, right? So that's 256 bits. Let's take it, let's load it, and do all the processing on it just on the vector register, right? Exactly the same thing as we would do on a scalar version, but this time on a wide register. Well, and no, you don't do that. It just doesn't work like that. The whole idea of the vectorized processing is that the data flows horizontally, data flows vertically. It's not a horizontal instruction which does something with one register. You need to work with a multitude of them. That's just a fundamental rule of vectorization. However, the benefit here is very clear. The memory system has its own latency, and both the cache system and the memory system have their latency. They work together to hide some of that, but if you have to run multiple memory access operations which deal with short elements compared to one operation which deals with the large access, that has a significant benefit, and significant it's times, sometimes tens of times. So if you look into the memory protocol, memory bus protocol, that's basically one transaction to transfer full cache line. The cache system operates only on a cache line granularity, and this happens to be exactly one cache line or half of a cache line. So if we really would like to use this for our benefit, but we cannot, well, let's look at the other ways. So we have multiple blocks in one message. Fine. Let's load those blocks separately into a multitude of registers over which we are running our vectorized SHA-2 algorithm. Looks nice in theory. We keep our benefits on memory access, but we fail again. And that's already on the algorithm level. The blocks have dependency one on the other. You cannot start calculating subsequent block until you have reached to the final state of the previous block. So we have a chain dependency. Can be made to work, and well, might be a fun interview question if you're really hard to interviewee, but that doesn't make any practical sense. Eventually, you will get at best throughput approaching towards 1 with latency being really bad. So it appears that the natural way to use this is to run multiple objects, calculating hashes over multiple objects at the same time. This means that you need to have first thing multiple separate different messages, multiple objects, and then you reapply that same idea. Take fragments of each and every message and run the calculation in parallel. Same algorithm, different data, exactly as the SIMD paradigm states. And what we have here, there's no cross-lane dependency, there's no cross-block dependency. It just flows vertically from top to the beginning. Now, this gives you some interesting properties, and cryptographers really would give you bonus points for that. This is constant time execution. Yes, constant time execution means worst execution relative to the length of, relative to the number of the blocks. But at least this doesn't leak you certain indicators of what your clear text data may look like. This is probably less applicable to hashing as such, much more applicable to the large number arithmetics and digital signatures and crypto things. However, this brings in some complexity. You need to handle those cases, and if your data length, if your data size is really non-uniformly distributed, you might need to do initial pre-sorting if you really care about the throughput performance. There's a difference in quantities of throughput and goodput. So if 15 of your messages are long and a 16th one is just one single block, or the other way around, you will have two extremes. You will be doing, in one case, mostly all of the work for goodput, while on the other end of the spectrum, only the tiny fraction of the useful work will be done all the time, and the rest will be just because you don't have any branching or any other control flow and divergence in the vectorized approach. And some surprising, excuse me, I'm sorry, wrong button again. So some surprising results might be observed in this, that this might even look better than, well, you would think theoretically possible. That's not a surprise. That's just the reality of how out-of-order execution platform works. Same as it reorders the scalar code flow, it does exactly same approach to the vector code. It does exactly the same zero idioms, for example, and other low-level hardware optimizations, which eventually can result in better than theoretically possible performance overall. What can we draw as a set of conclusions out of this SHA-2 example? First, memory is both painful and important. If you do bad things or if you are not in a friendly terms with your memory system, don't expect good performance. And the general approach to having good performance with memory is to operate on as large block relative to the cache line as possible. If you try to assemble your vector out of a tiny elements, just don't expect that the performance will be there. Load up the large block, including the parts of elements which you don't need, and then do the horizontal operations on registers to, well, shuffle and rearrange the data to the form that you will eventually need. Don't be afraid of throwing away a certain portion of data that is not needed for your immediate calculations. Eventually, the end result will be more performant than if you did that, well, in a maximum precision level. The hard part about the vectorization is handling all sorts of exception cases, not exceptions in a direct hardware sense, but the corner cases where you have where you need to do equivalence of the control flow branching. Now, if we try to look into the overall performance differences between the scalar, accelerated, and vector approaches, they all perform, and you certainly, it's for you to choose the application domain. If you need to run this on one message or on one object, acceleration might be the right option. You lose on the throughput, but you don't care about the throughput because you have only one element. On the other hand, if you have a multitude of elements which you need to process, eventually it might be that it is much easier to do that on the vector side. So, moving to another frequently used construct, the hash map or hash table. We can logically split that into two parts. So we have our initial objects, we have the hash function which runs over those objects, that's memory access. Hash function does typically something rather trivial on the compute level, and it provides you the location in the storage, however that is formed, where that element should go. So naturally, hash function is the first candidate for vectorization, and that is a good choice, yes. We previously saw that a rather complex hash function can be vectorized. The more trivial it is, the easier, as a rule, it is to vectorize that. You need to be aware of hazards, and the first hazard is multiplication, and all sorts of instructions which eventually make your result wider than your initial operands. Now, once you have got the hash value and you know where to place your objects, the fun part starts. That's, again, memory access, and memory access not in the most friendly pattern. You certainly can do that both theoretically and practically on a native vector code, but the big question that you should raise to yourself is, does that make sense? And in most practical cases, it doesn't. Therefore, the hybrid approach where you run your hash calculation in a vector way and then you just sequentially iterate over your storage where to place the objects eventually results in a better overall performance. And don't be misled by micro-benchmarking. As a rule, micro-benchmark in this case will show you that the vector-only approach is at least not worse, and sometimes maybe multiple times better. But once you are running a sufficiently large and sophisticated system which puts a significant amount of pressure on the caching system, things start to change dramatically. And therefore, the derivative outcome of all of this is that you should not abuse vectorization. Yes, it's a tool. Just the fact that you can use it does not necessarily mean that you should use it everywhere. Trees. Surprisingly, here we can also find things that can be vectorized. First thing, trees comes in a multitude of different flavors and types, and it depends whether there's a binary tree, there's a multi-way tree, and there's a radix tree, and all sorts of other things. Again, it comes down into translating the control flow branching into some form of data-based divergence or masking of the unneeded operations. In the networking world, trees are typically used for looking up addresses, IP addresses, Ethernet addresses, all sorts of other addresses, and one of the common cases there is what is called a multi-way radix tree. Where you have lookups based not on one single bit but on the intervals of bits. So here you can run into the same problems of accessing small fragments of elements which you later need to make a decision on, and typically that works with pointers. On a contemporary platform, the pointer, while on a logical side less than 64, but the full storage required for that is 64 bits. And that is quite expensive from the vector lane usability point of view. You do rather simple logical operations, you don't do multiplication, but yet you have to burn wide vector lane. The complexity here lies in trying to find a way of how you can do the full width address arithmetics based on the narrow length. So basically you split the 64-bit pointer into two parts and do operations sequentially with some magic. Apart from that, again, the same concept that if you want to look up or insert multiple elements in a bulk into the tree, vectorization-based approach may help you. If you have one element and you have to, well, look up the tree, then do something else, and yet something else, and then look up something in that same tree, and then something else and something else, don't look into vectorization. Overall, the performance in a scalar-like approach will be significantly better. Large integers, the joy of cryptographers and cryptography users. It's tempting to use vector registers again horizontally. We have many hundreds of bits, so we load up the full large integer and we expect that things will just happen. Well, unfortunately, no. There are certain red lines that you cannot cross within the vector boundary. Operations across the lanes, yes, some of them are defined, but that's a small fraction of those. It's very platform specific. Therefore, you need to change your algorithm approach if you want to apply the vectorization approach to this. And the overall concept, same as used in the scalar domain, that's a move to the notion of so-called limbs, where you split the large integer into small fragments, not necessarily multiple of 32 or 64 bits, but into some other quantities which are friendly to multiplication, to some other arithmetical operations. And then you load up your data in large chunks, do the transposition and reshuffling them already in a vector domain. The key important aspect to remember here is load as large object as possible, then chop off the parts that are not needed. Memory operations are far more costlier than a multitude of register-to-register vector operations. Those are relatively inexpensive. Again, the joy of cryptographer, the constant time operation. Regardless of what actual value of those large numbers is, your overall vectorized say multiplication or inversion or some other large number arithmetic operation will run in a constant time, which is equal to the longest one for each of the elements. That's not fully, in a strict sense, constant time operation. Well, if you have all zeros as an example, or on a finite field, all elements which eventually turn into the equivalent of 1, you will have different and very noticeable from external observation runtime. But if the data is realistic, again, practical, everyday, where you have it spread around and a sufficient level of randomness there, the overall runtime is constant, and you cannot infer much about each and individual of those large numbers that you are dealing with. And again, as a practical application of this, and which was kind of the whole story behind of this, moving into a networking world, BGP, and a derivative of its BGPsec. The security, the signatures applied to the announcements of BGP. Nothing complex from the algorithmic point of view. We get an update, we calculate a multitude of hashes, we sign those hashes and send the things out. On the receive side, we receive, we calculate the hash, verify the signature. If signature matches, everything is fine. If signature doesn't match, we complain and ignore this update. Now the complexity of this is in the scaling of the numbers. If we look at a global routing system today, that's on the order of 1 million prefixes. If you are a reasonable size, medium moderate size exchange, you might have 100 pairs there. So this already means on the order of 10 million prefixes. The average AS path length is between, well, 5 to 8, depending where you are in the network. We are coming closer to 100 million of signatures to be verified. And for the send side, it's typically the famous n-squared problem that we need to send out to everyone except of from whom we receive that, and we're easily talking about thousands of billions of signature and hash calculations needed for the full routing table convergence. Where vectorization helps? Well, we apply the same construct. We run hash calculation in parallel. We do one pass through the data, just cut out and reuse the data which we already accessed from a memory. And again, looking from a practical point of view, the cost of this is dominated by the memory access. If you need to touch memory multiple times, you have done something really wrong. Retain that. Load more than you need at once, retain that, and reuse it later. So the green vertical bars indicate just that. We are running the hash calculation over the same set of data, just the length of those blocks is different for each and every signature. Then we get a hash, we get a multitude of crypto parameters, keys, and whatnot. We run exactly the same basically it's elliptic curve crypto system, so large integer operations, and that just works. So you trade roughly 20% of the latency. It's a little bit slower, but your throughput is orders of magnitude higher than you would have otherwise. So where's the complexity of all of this, and why our good friend compiler cannot do this for us? It all comes down to the fact that you need to have efficient horizontal operation support, and your data layout needs to be friendly for this. All of that, from a technical point of view, from a hardware implementation point of view, that is present there in one or the other shape. That's usable. However, using that is a really complex task. And just the code transformation, what a compiler can do, it's insufficient. There are some research/prototyping projects related to what is called a multi-layer intermediate representation, where if you are familiar with internals of a compiler, that they translate the initial code into some internal representation, and then that internal representation is driven into the actual binary code. So this process is slightly divided in two parts. The first layer provides something like an intent type of hints of what this on the algorithm level is supposed to do, and then the lower level is actually dealing with the code generation. That's still on a highly experimental side of the things. So what's remaining? Over the time, sometimes funny, sometimes say kludgy type of solutions have appeared, or maybe just a hypothesis. What about atomicity? Right? If I have multitude of locks, and I don't want to deal with controlling the sequencing of taking those locks. Can I acquire multiple locks atomically with the help of vector approach? Looks nice in theory, however, that doesn't work. There are no guarantees about the memory ordering and atomicity related to the vector operations, for good reasons. That would add unjustified complexity and would basically break the total store order of x86 for backwards compatibility. So no, that's not possible, and that is not going to be possible. Therefore, you still need to care about the locking yourself. Overall, the ecosystem is fragmented, and it is getting more fragmented. We see a certain level of a marketing differentiation from the vendors, that certain functionality is available only on certain platforms, and that results in really different code paths and eventually systems that need to be maintained that will actually stay. Another important aspect to remember that the general rules of x86 platform execution apply. So speculative execution, data reordering, things related to memory operation are still required. So some controversial topics, and I think I need to cover only one. There's rather bad publicity about vector implementations in the field. And that has some historical reason for that, not excluding the misinterpretation of the facts. However, the laws of physics still apply. If you are producing more work over the instant of time, you will require more energy in one or other form in order to do that. This is a technological limitation. In the graph, you can see the performance degradation of a different generations of the compute platforms. It wouldn't get completely flat over time, but it is approaching much less level of degradation overall. This is purely the technology limitation. With this, I have mostly finished my part of spreading the propaganda from a stage, and I would like to then, try to initiate a bidirectional discussion in the forms of questions or answers or anything else about what I was talking here, right? I think I'm done with my part, and I already see our lovely host.
Thank you, Ignas. We do have. Thank you very much. Do you have any questions? For those of us who are here, you can ask a question with a mic. For our online participants, we have a special Telegram chat where you can ask a question, and I will speak it to our lovely speaker. Here we have a QR code to rate the talk and QR code for our Telegram chat. So please, anyone?
So I guess
don't forget, we have a special gift for a person with the best question. Maybe that will force you to ask something. Yes, please.
Hi, Ignas. Thank you for your talk. I have one question. Can you provide any examples of bad performance that you had after you attempted to implement vectorization in your real practical life?
All right, so I would say there are two areas related to this. One is memory access, suboptimal memory access, and that's, say, mostly obviously noticeable, right? You try to gather really tiny elements, thinking that this way you will optimize the memory bandwidth, but you actually just break the things, right? Because you need to open multiple rows and do all sorts of crazy things which have really large cost. The other thing is mostly on the algorithmical level, right? You can do the same task in multiple approaches, right? And that's basically the algorithm choice. Sometimes you will get surprising results of what a compiler thinks is less expensive than it is in a reality. Sometimes you yourself choose really suboptimal approaches to that. So, and I will probably mention the third area of problems, and that's not only the performance but also the functionality. The overall support of vector types, I would say, I would wish it was better in a compiler infrastructure. It works in most of the cases, but in some corner cases, there are really obscure problems which surface with a specific set of data at a specific amount of surrounding state and things like that. But to your question about the performance, memory. Memory system, right? Be friends with your memory and everything will be fine with your performance.
Thank you. Anyone else?
Right, there's somebody over there.
Well, thank you for your talk. I have a pretty weird question. Did you ever encounter any type of interference between different types of vector instructions? For example, we have some outdated code that use SSE and much newer that use AVX2 or AVX512. Are there any encounters where one would interfere with another in some sort of bad way?
Short answer is yes, definitely, and that's even documented in official vendor documentation. So you need to look from a historical perspective. What was state of the art at the times of SSE is not necessarily even close to being reasonable at the time frame of AVX512, right? Yet even it has backwards compatibility. Compiler typically is rather good at noticing these cases, or at least trying to recover from those cases, but not always. And sometimes things break in a subtle way. Overall, you don't want to mix it. Instead, have completely separate code paths. However that is implemented, separate loadable object, completely separate executable module, different code paths within. One of the reasons is that the interdependency between the registers and all sorts of internal machinery, right? Especially if we're talking SSE to AVX transitions and things like that. The other aspect is the vector overall vector length. You want your data structures to align with the vector length. And that means you will eventually have different data structures for different vectorization implementations. So if you want optimal performance on AVX512, and on AVX2, you cannot use the same data structure. It will be suboptimal for both. So, yes, summarizing, there are problems. Those problems, although, are quite well documented, so you just need to be aware of that.
We have no questions online, and no, 1, 2, 3, and no questions here. So, thank you very much, Ignas. Who made the best question, to your opinion?
Well, the best question. So, can we actually split the price in half and one half to one author, the other to? Oh, unfortunately, no. So, tough choice. I think that the memory one excuse me, not the memory one, but the different vector types has some well, importance embedded into that. So therefore, I would vote for the difference, for the different vectorization types question. So the gentleman over there.
Gentleman over the right. So, thank you very much. Right. We have a special gift for you as well. Please.
I think my special gift is so special that it is not here, and I will have to collect it myself. No,
maybe.
All right,
okay.
right. So, well, I will happily do that. Thanks so much.
Thank you. A round of applause
right,
for
thank
our
you.
speaker.